Okay, good day everyone. So the last presentation before questions and tea. I hope I can keep your attention. So this project, you might find some similarity to what we did on Tuesday. This project was specifically focused, or this talk was focused on the initial work, and then just at the end, just include a little bit of what we've done more recently. A quick look at an outline. I'm going to spend some time on an introduction. In this introduction, I want to add slides, but what we really experienced over the last few years, which I would like to convey to the industry, which I think is important. And then just a quick look at materials and methods, and then obviously focus on our findings and the conclusion. Okay, so when we talk about chlorine or chlorine products in industry, what we want to replace or what we're concerned about is calcium and sodium hypochlorite. You might know it as pool chlorine, or in the state of sodium hypochlorite as bleach. But I just want to focus on what's good, what we know what's good about the sanitizer. We know it's effective. We know it's inexpensive. It's quite available, and it's easy to apply. So these benefits we need to consider when we look for an alternative, because it also would ideally like to match these requirements. Unfortunately, the bad side is these chlorines produce byproducts, and these byproducts are obviously then toxic to your cell or genetic material, and that obviously creates fear, especially for the UK and the EU, which we then fear they might reduce the use of chlorine. Alternative, just announced something else to add is we also would like to identify something that's less corrosive in our packhouses in general. So I just want to make sure you know, so not all chlorines are created equally. So we need to just make sure if it's got chlorine in it in the molecule, don't think they'll all be as effective or produce the same byproducts. And that leads me to this slide. So I drew up this pyramid. I hope it looks like a pyramid. But when we deal with sanitizers or chemicals in general, we need to understand why is it effective, right? Chemistry is not magic. It's something that it's affected by external conditions. These four factors being quite primary. Looking at your product, you need to consider what's the stability of your product, what's the mode of action, what's the concentration of this product when you apply for your efficacy. Your environmental conditions is probably quite common to us. When we deal with chlorine, pH is very crucial. Ideally wanting your chlorine and calcium chloride form to be at pH 5.5 to 6.5. They can tolerate lower pHs, but never something above 7. And if you're dealing with water, for instance, out of Oranje rivier, you might hit pHs like 8, and then it will require additional treatment for your product to be effective. And then just the pathogen. So not all pathogens will the product won't be as effective against all pathogens. So the same type of pathogens. So it's quite easy, if I can say it in these terms, it's easier to kill botrytis than it is to kill Alternaria penicillin. And be lucky, you don't need to kill Aspergillus. Some tests we've done, we found that a rapid kill rate was needed 400 ppm of chlorine to be as effective, where 100 ppm for Alternaria was effective. Okay, and just lastly, time. And time is quite crucial when you look at contact time between your product and your pathogen. So please remember this when you deal with any chemical, but sanitizers specifically. Okay, so this is the alternatives we tend to look at when we looked for for what we want to include in the project. Some being just other forms of chlorine. We looked at ozone, just some of the hydrogen peroxide products, which is also not a chlorine product, but also can be quite corrosive. And then a bunch of inorganic salts or organic acids and so on. So this led us obviously to our aim to find these alternatives to apply to our POM industry. Okay, just a quick look at our materials and methods. So thanks to Fruitways, I think, and TrueCape for helping us identify some of our products, and then also to source some of our water to do some of our tests. After finding our products, we went into the lab. We just did a few in vitro tests. We looked at efficacy against different pathogens, primarily botrytis penicillin in the initial project, but also included Alternaria in our second project. And there we looked at our product concentration, spore concentration, and we looked at contact time. And based on that, we also combined some of these products that did quite well in combination with chlorine to see if we can just reduce the use of chlorine in general. And then those products were then, some of them were tested against packhouse water. We tested source water and Flume water, specifically contaminated Flume water in that case, to see if we what's the state of that water and can we sanitize it. And then lastly, just some trials in vivo on our fruit. So just for the first project, this is the products we came up with. Just from a quick point of view, those 3 products performed well against botrytis, but only one did well against botrytis and penicillin. That's our peracetic acid combination with hydrogen peroxide. Okay, so that's just a quick initial blimp indication. So, but going through the data, this is against penicillin. So penicillin worked quite well as a model organism to test sanitizers, and in this case, like I mentioned, your peracetic acid and hydrogen peroxide did well, but none of the other sanitizers we used. Obviously chlorine at the end doing also what it had to do. Okay, and then against botrytis, you can see there's a bit more products to include. Your ascorbic acid doing quite well, and fulvic acid, the F there, requiring quite a high concentration to be effective. Okay, so just combining it with a low dose of chlorine. In this case, it's literally like 30 ppm of chlorine. It's very low. We saw some improvement when we combine it with chlorine against penicillin, specifically referring to the lower dose of even the peracetic acid and hydrogen peroxide. And then looking at botrytis, again, seeing some benefit in including a low dose of your chlorine, if that was an option going forward. Okay, so this is quite interesting. This is the packhouse water. So we included 5 packhouses, but I'm only going to include results from 4. So this is packhouse water that looked quite well. The F there is just the Flume water, so with nothing added. We realized later on we had to spike some of this water to find results to see if the product is going to be effective. So that plus B means addition of botrytis spores, and the plus P includes the addition of penicillin spores. So your Flume water in this case was quite clean based on your untreated results. There were no colonies detected. When we spiked it with penicillin, we saw that again, the peracetic acid and hydrogen peroxide doing well, but we can't really say that about the other sanitizers. Okay, in this case, the packhouse water was super treated. It doesn't matter what we added to the water, it killed everything in there. So obviously nothing to produce from results side, but I mean obviously water that was properly treated. This is what you want to see. Okay, and this is packhouse or Flume water that didn't do very well, although it's not the worst case. And that's obviously based on our untreated control. So this obviously would then render good results to us. And here we saw all treatments doing quite well. Remember, this is Flume water, so this contains all organisms. It's not just botrytis and penicillin, so it brought down the counts quite a bit. And then looking to spiked water, again, it's the same products coming out, your ascorbic acid, your fulvic acid, your hydrogen peroxide with peracetic acid. And penicillin, again, just the one showing. And this is even worse water. So this packhouse didn't have very good quality water, so always just keep in mind. Obviously, when we sourced this water, it was water that was used for like 3 days already, so we want it to be contaminated. In that case, also we see that from the untreated, that it's bad quality Flume water. Seeing same results. In this case, your hydrogen peroxide and your peracetic acid doing well, your ascorbic acid doing at your double concentration, showing something or not very effective. And then adding botrytis is quite similar to the just with Flume water alone, and the penicillin requiring just the one product, and again working. Okay, this is results on fruit. So the fruit results we need to consider is inoculated. So to inoculate fruit and treat it with sanitizers is not ideal. The sanitizers tend to struggle a lot to solve the inoculation, even if it's dipped quite recently after inoculation. And then also to remember here, the contact time is just 5 minutes. Okay, but regardless of that, we saw chlorine doing very well in this instance, but the hydrogen peroxide and peracetic acid even outperforming your chlorine, so doing very well. Okay, so in conclusion for this project, we saw hydrogen peroxide and peracetic acid combination doing very well. However, unfortunately, this product it's got quite a volatile smell. It's got a strong, a pungent vinegar-like odor, which is not recommended in indoor environments. An additional requirement is we did not pick out any phytotoxic effect, but dealing with cultivars like a Fuji or a Honeycrisp or a Gala that might be sensitive to some burn or lenticel damage, this might be something to consider to test against. So there might be concern in this case. We didn't explore that avenue. So just be cautious when you consider this product. And looking at botrytis, obviously we've got more products, but this is quite regardless because we need to treat penicillin and Alternaria in our pack houses. So that last point there, I just want to make mention, why do we want to sanitize? Because sometimes it feels like we want to sanitize the water, and our aim in doing that and sanitizing fruit's not the same. So keep in mind when you start dipping your fruit, and it's high contaminated fruit, and it's a high processing time, the contact time can be compromised, and the amount of organic matter in your water will be affected. So always be sure what you're doing and what's the requirement. It's not just to sanitize your water, but your fruit as well. And a high contaminated fruit will always require some additional consideration. And please remember, if your fruit's already infected, the sanitizer is not going to help you. It can't cure. Okay, so, sorry. Just the project 2. So if you sat in on Tuesday, you saw some of these results. So the project 2 included a further, I think it's 9 products. 6 of those products performed well against botrytis. Against botrytis, penicillin, Alternaria, it was only the ionized water, the ozone, and a product called hypochloric acid doing quite well. A lot of attention on that last one. I don't have a lot of slides. How much time do I have? A lot of time. So I included here just a slide from penicillin, just to indicate. So here the bars has changed. So apologies for that. And the previous one is about the amount of colonies. Here it's about efficacy. So the higher, the better. So here we see the effect of ionized water requiring a high concentration to be effective. Your ozone doing quite well across all concentrations, all effects, and then your hypochloric acid doing, again, also very well. Okay, so that's one to focus on. It is a chlorine-based product, but it's not a chlorine-based in the sense of no calcium or sodium hypochlorite. It doesn't act the same. Its molecule is quite different. It's got a neutral charge, which implies it's easily absorbed by the pathogen, giving it additional effect. It's also a product that's been reported to be non-toxic, so something really to look out for. Just the time scale here, ionized water doing well, ionized water and chlorine actually being effective within 3 to 5 minutes, but again your hypochloric acid doing well within a 1 minute. You got a kill effect against penicillin. So in conclusion, here we've got an additional of ozone and your hypochlorous acid to work with, a broader range to work with botrytis, but again, focus being penicillin Alternaria. So now we need to consider where are we going about with what we're going to do next. We're going to have to look at efficacy. How corrosive is this product? Although literature has proved, because it's used in medical sciences to treat wounds, to treat eyes, to treat skincare products. They even use it in use of eczema. It's included in cosmetics. It's included in baby products. I don't know the concentration of the product in those products, but it indicates to us that it's something that's not very corrosive. Its pH is at 6, so doesn't have a low pH, so it's not corrosive in that sense. This product is produced from table salt. So in some cases, there's a speculation that if corrosion is picked up, it's potential that a low amount of salt is coming through. And that might accumulate in your Flume tanks, and that might have a negative effect. So it's all things we have to look at going forward. And that's me. I'm sorry if I'm too quick.